Now we're going to talk about Dennard scaling. And this may not be something you've heard about before, but you're going to see that it's become a really serious problem now that it's come to an end. So one thing you probably have seen before is Moore's law. And let's refresh ourselves, what is Moore's law? What does it say? Well, Moore's law says that the number of transistors per chip doubles every 18 months. It doesn't say anything about the speed. So here's what Moore said. Here's from his original paper. He had 5 data points, and he predicted based on those 5 data points that for the rest of eternity, things would keep doubling. And this is, of course, ludicrous. I mean, anybody reasonable should look at this paper and say, this is nuts. You know, this isn't going to happen. And in fact, if it hadn't kept happening, people would probably have ignored this paper. So let's see how well he did. Here's the part of the data that Moore predicted for, and the data he analyzed was right down here, and he predicted this trend. And he got it right, exactly right. So whether it was luck or brilliance, he really figured this out. He hit the nail on the head. And so this is why Moore's law is so famous, because based on this teeny little bit about here, he predicted an incredibly long trend here. But Moore's law by itself isn't all that exciting. The really interesting thing is the corollary. This is called Dennard's scaling. And what he did was he looked at this in 1974, and he looked at scaling trends, and he figured out what this implied for the future if devices kept scaling by this amount. So he said, assuming that everything gets 1 over k smaller, how are things going to change? And this was the conclusions he came up with. So he said, if the device dimensions keep going down by 1 over k, that is, things there keep getting smaller, and we can keep increasing the doping concentrations by that same k, so that is, we can put more ions in there so that we get the same effect, and we can keep reducing the voltage by 1 over k. We can do all of that stuff, then the following nice things happen. The delay for the circuit, that is the speed of our transistors, is going to go down by 1 over k. Well, that's fantastic. You know, we make things smaller and they go faster. And the power dissipation is going to go down by 1 over k squared. That's, you know, fantastic squared. It means we get more transistors and they're costing us a lot less power each. So what Dennard said here was that as long as these things are true for scaling, we get these things sort of for free. And these are fantastic because it says our transistors get to run faster for free and they take less power. And this combination means that the overall power density, that is the power that we have in a chip, stays the same. And if it stays the same, that means we can just take advantage of these things forever. Of course, this requires that these things continue to be true. So now we have to get to the question, was this really too good to be true? Well, we'll see that it has come to an end, but for a long time it was truly fantastic. So what Dennard's insights and Moore's insights put together is they said that every 18 months we can put twice as many transistors on a chip. Those transistors can run twice as fast, can increase our frequency, and they use 1/4 the power. So put together, this is why Moore's law is so impressive, because we get both the scaling and the performance out of it. So let's take a look at what this implies. So what does this imply if I double the frequency and the number of transistors every 18 months? Well, it implies that chip power stays the same. So 2 times the transistors, 2 times the frequency, that should, you know, double the power, but it's 1/4 the power per transistor. So I get the same. And this is truly amazing. This says that Moore's law lets us build more stuff, but Dennard scaling says that we're going to get better performance out of that stuff constantly. So this was really amazing, and this is what led to the incredible growth of microelectronics. So, of course, anything this good, and this was really good, can't last forever, and we ran into some limits here. So we're running into physical doping limits. As gates get really small, there just isn't a lot of space to put in atoms. So it's really hard to keep increasing the doping density. We had a problem with human greed. We kept pushing frequency much faster. Remember, Dennard said that we could increase frequency of 1 over k. And well, we could get a little bit more if we paid a little bit more power, and that little bit more added up over time. So we pushed frequency a lot harder. And finally, we're running into voltage limits. So silicon has this sort of fundamental property of the atoms that it's got a threshold voltage of 0.6 volts. And if you get transistors down to close to this voltage, they behave very badly. Well, they behave very differently. You can build circuits below this, but the traditional way of building circuits doesn't work here. So this is really putting a limit on how low we can make the voltage. So let's take a look at this with some data. So here's some data about what's happened with transistors. So we've seen the transistors keep getting smaller over time. That's great, logarithmic scale. This is what we'd expect, 1 over k gives us a nice linear plot here. But the voltage isn't keeping pace. So here's voltage. You can see we're getting a bigger and bigger difference. The rate of decrease of voltage is not the same as the rate of decrease of size. And Dennard said that we only get this really nice trend if we keep these together. And the result of this is that power doesn't stay nice and constant, particularly since we're increasing frequency at the same time. So this is this huge increase in frequency, and it's largely driven by this difference here. Our voltage is not keeping up with our scaling size, and we continue to push frequency up. So we're not going to get more and more gigahertz because we have problems with the power due to the fact we can't lower the voltage. So we've been looking at multi-cores instead. So multiple chips that run less fast, which means we've had lesser performance benefit, and it's much harder to get performance out of multi-cores. So we all know if you get 4 cores, you don't run 4 times as fast. What these trends have led to is that today everyone focuses on power. This has become the key constraint for doing things. In fact, if you look at Intel's Haswell designs, they explicitly came out and said they put a 2-to-1 premium on power over performance. This means that if you came up with a design that said it gives you 10% better performance, it had better not use more than 5% power, because power is more important than getting performance. Here's another way to look at this. So here's some more data here, and it plots for a bunch of years here the number of transistors, and you can see here's Moore's law going steady, exponential increase in transistors. Here's the relative performance. The relative performance leveled off about 2005, didn't keep getting higher. Here's the clock speed. Clock speed leveled off there, and the clock speed leveled off because we couldn't reduce the voltage, so the power was getting too high. So that meant we were limited on the frequency. And the reason for this was the power. We couldn't cool the things because the voltage wasn't going down enough. And this is what's been known as the power wall. It says that we can't go beyond this because it's too expensive to cool things beyond this, and we're not getting the scaling we expect because we can't reduce the voltage. So the result of this was this trend here in the number of cores. We've now got multi-core processors. So we still get more transistors, we just can't run them at a higher frequency, so we have to do something with them to make money, and what chip manufacturers do is they put more cores on the chip. Alright, so what is the driver for this end of Dennard scaling? What is the thing that's really made it come to an end? Well, the main thing is we can't lower the voltage. So we can still build faster circuits, and we can still make them smaller. We can even make larger chips, it just costs more money, but it's lowering the voltage that we can't do. And when we can't lower the voltage, Dennard's great thing about not increasing the power stops being true.